Welcome to time complexity. In this video, you'll learn about time complexity and how is it used to denote the efficiency of algorithms. So what is time complexity? Time complexity is essentially the amount of time that it takes for our algorithm to run. So in short, it's the run time of our algorithms. So what is an algorithm? In general, an algorithm is a program that takes in the input. It does some computations, and then it returns an output. So this is the main part which we're focusing on for runtime. It's the amount of computations it'll take for us to run our algorithm. So we can use this to make a graph of our time complexity. So we have our x-axis and y-axis, and then we need to label these. So our x-axis is going to be our inputs, or input size, and this is denoted by n. And then we go to this side. We have our computations. Well, I can't. We have our computations. And then this is essentially our time. So we have our input size and then our computations, which is our time. So there's 5 main things that we need to know about our time complexity. The first one is constant time. So if you remember from algebra, a constant, it just looks like a straight line on a graph. We'll call this constant. This means that no matter our input size, our computations are going to be the exact same. So it'll never change, which means it's constant. And the next one is going to be linear time. We'll do linear. We'll just skip some of them. We'll come back to the other ones later. So linear time, it's just a straight line. How steep should I put it? Right. So linear time. This essentially means that our number of computations will be proportional to our input size. This is our second best one. Constant always going to be our fastest. Linear is usually going to be our second best bet. And the next one we're going to do is quadratic time. So quadratic time is just, that might not be the best drawing for that, but it's fine. Quadratic. So quadratic just means that it's our input size, and then the computations is our input size times the input size. So we'll get n squared, which is quadratic. The next one we'll get into, or the next 4 that we do are like less common than these ones. These are going to be our 3 most used ones in like LeetCode questions and stuff like that. But we'll go into like the special ones too. So the next one that we'll do is logarithmic time. And logarithmic time looks something like this. I'll just call it log time. And if you remember from math class, log time just means, let's write this. So our time equals to the log base 10 of n. So that's how much time or how many number of computations that'll take. And we'll get into examples of all of these in later videos, but right now I just want to show you the different time complexities that our algorithms can have. And another one that could build on top of linear time, or not log time, is log linear time. which looks like this. Kind of looks like that. And we'll call this log linear. So this might not make that much sense right now, but when we get into the next part of the video, all of this will make sense. So let's just get into the next two. So there's two more that are the most common, and that's exponential and factorial time. Exponential looks like this. I'll just shorten expo, it's fine. So exponential time, if you remember from math class, is be like something like 2 to the n. So this 2 can be changed up, but usually that's like our base. So 2 to the n, that's our exponential time. And then we'll get into factorial time. Factorial time is going to be our worst one. So you can see a little pattern on this graph. So as the lines get steeper and steeper, the more time that it takes based on our input size. So our goal on any algorithm or LeetCode question is to minimize our time complexity. So our goal is to bring it to like this side of the graph somewhere. And you don't need to worry about it too much, because some problems, their best solution can be like up here too. So you also have to think about that. Sometimes it's not possible for us to go down here in the time complexity graph. So for questions like all permutations of a list, factorial time is basically the fastest time that we can get. So this is also important to learn. So the next part of our video is how to denote the efficiencies of our algorithms. And this is a really important topic that we'll get into with our technical interviews and all the LeetCode questions that we need to solve. So you need to be able to denote the efficiency of an algorithm. So to denote the efficiency of an algorithm, we'll get into big O notation. Big O notation. So basically, big O notation is a way to write our graphs in a shortened version. So let's take linear time, for example. In math class, you'll learn that linear is equal to y equals x. So let's just say linear equals y equal to x. But here, our input size is denoted with the variable n. So if we change this to y equals n, we'll still have the same thing because this is a different variable. And this is shortened by, with big O notation, is called big O of n. So that's essentially what it means. Big O of n just means the amount of time that it takes based on our input, and we usually just denote that by a big O. Then in parentheses we'll put our variable in there. So that's our linear. So if we move, all right, let's just go to constant first. So constant is pretty easy. Constant is just big O to the 1, because, oh yeah, one more thing that we need to go before we write down all the time complexities. So the one thing that we need to notice, that constant, it's always going to be big O to the 1, because we're looking at the lower bound of our graphs. So if our constant shifts up to, like, say 5 up here, it'll still be O to the 1, because we don't care about the extras. So O to the 5 is just equal to O to the 1. And same with O to the n. And if you remember in math class, we learned like y equals mx plus b. We don't care about the m or the b, because we don't care about the shifts of the graph. So let's say we have y equals 2x plus like 3. And in big O notation, that would be O to the 2n plus 3. We can just say that's O to the n, because we don't care about the shift in the graph, and we don't care about the b. So yeah, we just don't care about any of the constants in our time complexities. So let's go to the next one. All right, we'll go in order. Log is just going to be O to the log n. And then we'll go, we already did linear, so we'll do log linear. Log linear essentially means, oh, I wrote it wrong. Alright, it's fine. So log linear is just O to the n log n. So you can see where we got our name from. It's just O to the n log n. And the next one we'll do is quadratic. So quadratic O to the n squared. And then exponential is expo is O to the 2 to the n. And then factorial is O to the n factorial. So these are basically all our common time complexities. O to the n, O to the 1, n log n squared, 2 to the n, and n factorial. And yeah, that's basically what the basics of time complexity is right now, and how to denote the efficiency of algorithm with big O to the notation. So this might not make a lot of sense right now, but I'll be uploading some more videos with example problems and more in-depth examples and programs of each of these notations. Thank you for watching.